In this BocaPhysics video, you'll see a set of simulations depicting the motion of a charged particle in the presence of a uniform magnetic field. In these simulations, we won't concern ourselves with how the magnetic field arises, only that it exists. The force that a charged particle experiences in the presence of a magnetic field is given by the Lorentz force law. Force is equal to charge times the cross product of the velocity vector and the magnetic field. And here we see the three vectors represented graphically. The green vector represents the magnetic field, the blue vector represents the velocity vector, and the yellow vector represents the force vector. We've assumed here that the particle in question is positive. So not only must the particle be in motion in order for it to experience a force, the magnetic field causes the particle to accelerate in a direction perpendicular to its motion. This is in stark contrast to the force that charged particles experience in the presence of an electric field, where force is equal to charge times electric field. A magnetic field cannot cause particles to speed up or slow down, but it can change a particle's direction. If there's an electric field in addition to the magnetic field, then the force is equal to charge times electric field plus charge times the cross product of the velocity vector and the magnetic field. In the first simulation, we see the motion of a charged particle that initially has velocity perpendicular to a uniform magnetic field. Let's assume that the particle carries a negative charge and that the magnetic field is directed out of the screen. The effect of the magnetic field is to give rise to a force that is perpendicular to the motion. Lorentz force serves as a centripetal force, causing the particle to travel in a circular path. And here we see the vectors drawn in. The green vector represents the magnetic field, the blue vector represents the velocity vector, the yellow vector represents the force vector. Notice that the green vector, magnetic field, is pointing in the same direction. The blue vector, or the velocity vector, is always tangential to the trajectory, and the yellow vector, or the force vector, is always pointing towards the center. From this viewpoint, the particle travels in a counterclockwise direction. The radius of the orbit, or Larmor radius, can be determined by setting mass times speed squared over r equal to the absolute value of the charge times the speed times the magnitude of the magnetic field. Hence, the radius of the orbit is mass times speed over absolute value of charge times magnitude of the magnetic field. The cyclotron frequency is defined as omega equal to absolute value of the charge times the magnitude of the magnetic field over the mass. A positively charged particle will gyrate in the opposite direction, that is to say, in the clockwise direction. In the second simulation, we see the motion of a charged particle that has a component that is parallel to the uniform magnetic field, as well as a component that is perpendicular to it. In this simulation, the magnetic field is directed upwards. The yellow pole is included so that you can better see the trajectory. The component of the velocity that is parallel to the magnetic field is unaffected by the Lorentz force. But regarding the component of velocity that is perpendicular to the magnetic field, the Lorentz force leads to circular motion. In other words, the trajectory of the particle is helical. In the third simulation, we have a particle that is initially at rest in the presence of a uniform magnetic field that is directed out of the screen and a uniform electric field that is directed upwards. Initially at rest, the particle does not experience a magnetic force, but is sped up by the electric field. Once in motion, the magnetic field acts on the particle, causing it to turn to the right as the particle continues to move upwards. Beyond the point at which the particle reaches its maximum height, the particle once again moves against the electric field and hence is slowed down. The magnetic field causes the particle to travel back to the x-axis, at which point it is at rest. Then the electric field accelerates the particle upwards and the whole process repeats itself. In this last simulation, different values of the electric field and magnetic field were chosen to make it easier to see how the particle slows down, is at rest at the cups, and then speeds up. Slowing down, at rest, and then speeding up. In this set of simulations, you have seen the three types of particle trajectories commonly discussed in undergraduate electromagnetism classes. In plasma physics, other more complicated types of motion are investigated. For example, the motion of a charged particle in the presence of a non-uniform magnetic field, and the motion in the presence of a time-varying electric field.